Less than 100 miles above our heads lies an unending universe which is vaster than we could ever comprehend. But it's far from empty. Instead, it's filled with incredible phenomena that our puny brains can barely grasp. Can you fathom the existence of things like stars within stars, planets made of diamonds, atom-sized black holes, or even white holes? Before you space out, let me bring you back to Earth with some intel about the great starry expanse that'll really blow your mind. The Earth isn't round. You've probably seen photos of Earth taken from space, showing that our planet is undeniably round. But looks can be deceiving, because this big blue marble isn't a perfect sphere. And before all the flat earthers chime in, no, it isn't a pancake either. As the planet spins, it creates a centrifugal force that's highest at the equator and almost nothing at its poles. Because the Earth's mass is distributed unevenly within it, the force drags the equatorial section of the Earth outwards. This gives the Earth a slightly squashed appearance, almost like someone accidentally sat on it. The effect, however, is small. So small that if you compared the diameter of Earth at the poles to the equator, you'd only see a 0.3% bigger latitudinal bulge. Even so, that's still a 26-mile hump, which is almost double the distance from the top of Mount Everest to the deepest parts of the Mariana Trench. Wow! That's almost as big as the lie those flat earthers tell themselves. Before the Flat Earth Army descend on the comment section of this video, help me fight back by hitting those like and subscribe buttons. Just one click on that thumbs up button gives this video more likes than a flat earther has IQ points. So don't just do it for me, do it in the name of science. The sun isn't burning. If any of you have been outside recently, pandemic permitting, you've probably felt the warm rays of the sun shining on your face. But despite the undeniable heat it gives out, this giant ball of hot gas isn't actually burning up. That's because the term burning refers to a chemical reaction involving the rearrangement of electrons in an atom. So the element itself does not change, but the arrangement of its electrons does. However, our sun, which is comprised primarily of hydrogen and helium gases, uses a process called nuclear fusion. That means instead of the atoms being rearranged, the very nature of the element changes. Instead of burning the hydrogen, the sun converts gigantic quantities of it into helium and energy. So much so that it releases approximately 300 million tons of energy a minute, which would be equivalent to exploding 100 billion tons of dynamite every second, according to NASA. Talk about a big bang. But this immense reaction requires an astronomical amount of heat and pressure, kind of like a star-sized pressure cooker. Except the pressure in this pot is equal to 250 billion times that of Earth's atmosphere, pushing the temperature at its core up to a staggering 30 million degrees Fahrenheit. It may not be burning, but a galactic kitchen producing that much heat is certainly one I'd like to stay away from. The heaviest thing in the solar system. Even though it's converting more and more of its finite fuel source into energy, the sun is still the heaviest thing in our solar system. And not by any small amount. It holds a whopping 99.85% of the solar system's entire mass. In comparison, all 8 planets combined make up a measly 0.135%. But wait, didn't I say before it's made up of gases like hydrogen and helium? How can lightweight fumes outweigh good old-fashioned solids? Well, the soul-crushing pressure making up this red-hot gas ball condenses most of the particles of the gas together at its core. Though the core makes up just 2% of its entire volume, it has a density which is about 15 times that of lead. This means it makes up an astonishing half of the sun's overall mass. So while it only has a diameter that's 109 times that of the Earth, it weighs approximately 333,000 times more. I'm sure there's an opportunity for a classic "your mom" joke in there somewhere. The heaviest star in the universe. Our sun may be incredibly heavy, but if it was preparing for a physical fight against the other stars in our universe, it'd be dumped in the lightweight category. Across the ring, sat at the top of the super heavyweight roster, would be the colossal yet uninspiringly named R136a1. Though it doesn't sound super imposing, this giant star is estimated to weigh 315 times that of our sun. For some perspective, that's almost 105 million Earths. But what is it that gives this star its super weighty edge? Well, if you were to train your telescopes about 163,000 light-years from Earth, you'd be able to feast your eyes on the horrifyingly named Tarantula Nebula. There, you'd see a brightly glowing Wolf-Rayet star. It's a rare class of star that carries huge amounts of ionized helium, carbon, and nitrogen. It's these super heavy elements that give the giant star its unimaginable mass and intense glow. So intense that if it were compared side by side to our sun, it would outshine it as much as our sun outshines the moon. With that said, I think we can all agree that against R136a1, our sun really has no weight in this competition. The biggest star in the universe. R136a1 may be incredibly heavy, but it's actually quite small. With a diameter just 35 times bigger than our sun, it's more like the Michelle to the universe's Beyoncé. And while Beyoncé may be the biggest star in the world, UY Scuti is the biggest star known to man. It's so mind-blowingly large that when compared to our sun on a computer screen, it barely makes up 1 pixel. But if it's so big, how come we're not constantly blinded by it? Fortunately for our eyes, it's situated in the Milky Way galaxy's Scutum constellation, around 5,219 light-years from Earth. But even though it's so far away, its incredible size makes it stand out from the small cluster of stars it's surrounded by. That's because UY Scuti tops out the tape measure with a radius that's a staggering 1,700 times larger than that of our sun's. That gives it a diameter of almost 1.47 billion miles across. So even if you were to travel at rocket speed, which is a breakneck 4.9 miles a second, it would still take you almost a decade to pass through. Or, if you prefer land vehicles, a non-stop 50 miles per hour trip would see you reach the other side in an inconceivable 3,371 years. I wonder what would wear down first, your tires or your sanity? Planet 9. If you were to travel beyond all the known planets in our solar system, you'd come to a cold, dark point in space known as the Kuiper Belt. Unlike the neat circular orbits of our planets, large objects in the Kuiper Belt have trajectories that seem a little lopsided at best. While they all still orbit the sun, you can see the most distant objects all swing out awkwardly in one direction. But according to the principles of astrophysics, this unevenness should be, for lack of a better word, impossible. However, scientists recently theorized that their crooked trajectories could make sense. That is, if there's a huge undiscovered planet swinging in the opposite direction, balancing them out. According to their calculations, this 9th planet would need to be about 10 times the mass of Earth. Considering its size, you might be wondering why we haven't already spotted it through our telescopes. But that can be explained by its mind-boggling orbit. For perspective, the furthest known planet from our sun is Neptune, at a staggering 2.8 billion miles away, circling the sun once every 165 years. But Planet 9's orbit would be 20 times that distance, taking an astronomical 10,000 to 20,000 years to make a single trip around the sun. But without any concrete images from satellites or telescopes, this phantom planet remains purely theoretical. What do you think? Does Planet X exist? Let me know down in the comments. The number of stars. Counting every single star in the sky sounds like an endless task. But with a little math, it's not too hard to figure out just how long this astronomical mission would take you. Let's start at a galaxy level, our own to be precise. Some calculations indicate our Milky Way galaxy holds between 100 to 400 billion stars. Using that as a jumping off point, next we need to figure out how many galaxies are in the universe. Seeing as we don't know how big the universe really is, this is a colossal question. However, one astronomer, named David Kornreich, has proposed a rough estimate of around a staggering 10 trillion different galaxies. Multiply that by our 100 billion stars per galaxy estimate, and you get approximately 1 septillion stars. That's a 1 with 24 zeros and a lot of stardust trailing behind it. So, now that we have a number, how long do you think it would take you to count every single star in the sky? Well, assuming you counted one a second, it would take you over 31 quadrillion years to pinpoint them all. As impossible as that mission sounds, I think we just discovered what the most mind-melting job at NASA might be. Spellbinding supernovas. As ethereal as they look, stars don't last forever, and when they die, they go out with a real bang. These astronomical explosions are called supernovas. They involve massive stars at least 8 times the mass of our own sun that consume huge amounts of hydrogen at their cores. The energy this produces generates an intense outward pressure, which prevents the star from collapsing under its own colossal gravity. But when the star runs out of fuel, gravity finally wins against the pressure, and the star collapses in on itself. It happens so suddenly that it would be like watching something a million times the mass of Earth collapse in just 15 seconds. As you can see from this NASA animation, the shockwaves this produces blast apart the outer layer of the doomed star. But unlike you may have imagined, they don't always explode so spherically. For proof, just take a look at supernova 1987A, located around 160,000 light-years from Earth. After it exploded in 1987, researchers were astonished to find that, instead of the spherical burst they'd expected, the blast had been faster and stronger in different directions. This has left the resulting starburst look like a bow tie from one direction and the eye of Sauron from another. What do you see? Bizarre black holes. While the remnants of some supernovae look otherworldly, others can leave behind something truly nightmare-inducing. If the remaining stellar cores of enormous exploded stars no longer have the outward force of heat pressure opposing their gravity, then the core collapses in on itself. This impossible-sounding occurrence is what we know as a black hole. However, it's not the same as watching a building collapse. Because a star caves in on itself, its rapidly reducing surface approaches a point called the event horizon. This is the threshold where the speed needed to escape the gravity of the collapsing star surpasses the speed of light. That means anything traveling under 186,000 miles per second is dragged in and consumed by this ever-collapsing gravity well. Without light, time around it slows to the rate that is kept by its observers. So this means it's an infinitely collapsing object forever frozen in time. But what exactly do they look like? You've probably seen films where black holes are portrayed as planet-sized voids, but what if I told you they could get much, much bigger than that? Well, sat 10.4 billion light-years away in the Abell 85 cluster, the black hole known as Ton 618 is calculated to have a mass 66 billion times that of our sun. And with great mass comes great size, meaning this black hole has a world-ending diameter of over 242 billion miles. For perspective, that's 2,606 times the distance from the Earth to the sun. It's no wonder it falls into the ominously named ultramassive black hole category. But if that incomprehensible scale blows your mind a little too hard, then shift your attention to the other end of the size spectrum. Unlike stars, black holes have no limit to how small they can be. With that said, scientists believe a black hole can be as small as a single atom, the smallest unit of ordinary matter that exists. But don't let it fool you. Even at this size, a black hole would have a relative mass that's as large as a mountain. So, unless you think you could take on Everest in a fistfight, I'd steer clear of these miniature gaps in reality. Weird white holes. While black holes hog all the limelight, their neglected twin white holes barely get any airtime at all. That's right, white holes are, as the name suggests, the theoretical opposites of black holes. As I previously mentioned, black holes have gravitational boundaries that can stop just about anything from escaping. Well, after some physicists fiddled with the maths back in the 1970s, they concluded that an opposite entity could exist that prevents anything from entering instead. So while a black hole gobbles up matter, a white hole spews matter out. It'd be an incredibly bright and energetic object, hurling energy into the depths of space at an astounding rate. But how on Earth would they form? Well, thankfully, not on Earth. All roads of this theory point to them forming in the reverse of their black hole brethren. So instead of collapsing in on themselves, a super dense singularity would vomit up matter until pop! It assembled itself into a star. However, this violates several fundamental rules of physics, and seeing as no white holes have been spotted in the known universe, they remain purely theoretical. Saying that, black holes were also just a theory until 1971, and that was only 50 years ago. Maybe in the next 50, a rogue white hole will shed some light on the matter. Sparkling showers. In some parts of the world, rain is incredibly precious, but on the outer planets of our systems, it's priceless. Not because it's rare, but because it literally rains diamonds. This incredible occurrence starts in the atmospheres of gas giants like Jupiter, Saturn, Uranus, and Neptune. All 4 planets have atmospheres that contain high quantities of methane. During lightning storms, the electrical energy converts the methane into soot, which clumps together and hardens into chunks of graphite. As the chunks get heavier, they're dragged down by the planet's gravity and into the ever-increasing pressure of its atmosphere. While they fall, the carbon atoms are compressed into incredibly sized diamonds, with some of the largest measuring about a centimeter in diameter. On planets like Saturn, these storms are so frequent that about 1,100 tons of these dazzling stones drop to the surface every year. Or, for perspective, just enough to make up one Met Gala outfit for J-Lo, by the looks of this OTT outfit. The Diamond Planet. When it comes to planets boasting copious amounts of diamonds, the previously mentioned gas giants can all step aside for 55 Cancri e. After the discovery of this super-Earth in the Cancri constellation back in 2004, scientists began analyzing its composition. They estimated that this carbon-abundant planet has a mass 8 times greater than Earth, with a radius only twice as wide. The discrepancy meant that the planet must be made of dense carbon compounds like graphite and, extraordinarily, diamond. But it wasn't just a few necklaces worth. Scientists theorized that a thick layer of pure diamonds coats the planet's inner layers, making up a staggering third of its mass. That sounds pretty valuable. In fact, if it were to be valued on its diamond content alone, it'd probably be worth approximately $26.9 million. That's 26.9 followed by 29 zeros. Although it sounds like an ultra-wealthy utopia, there's nothing cool about it, literally. In fact, the temperature of the surface reaches a flesh-melting 3,900 degrees Fahrenheit. The inhospitable environment makes this planet an extraterrestrial diamond in the rough. The hexagonal hurricane. At school, you probably learned that the most amazing feature of Saturn was its stunning set of rings. But if you look closer, you'll see an even more mind-blowing side to this planet, or 6 to be precise. At the north pole of this serene-looking gas giant, a huge hexagonal storm is constantly raging. It was first discovered in 1988 in footage from the Voyager probes, and additional visits from the Cassini probe in 2004 has revealed inconceivable details about the six-sided storm. From thermal images, researchers estimate it's about 20,000 miles wide and 60 miles deep. with winds whipping around at approximately 220 miles per hour. But how do all these elements fit together to produce a perfect polygon? After all, the universe doesn't normally build in such straight lines. Well, using all this information, researchers attempted to recreate the oddly shaped storm in computer simulations. By adding in small perturbations to the planet's eastward airflow around the North Pole, they found the currents jostled with one another and meandered into a hexagonal shape. I guess the universe wasn't cutting any corners when it whipped up this phenomenon. Amazing auroras. Have you ever witnessed Earth's greatest light show? And no, I'm not talking about Americans turning on their insane Christmas displays. As bright and garish as they look, they'll never compare to the North Pole's all-natural illuminations. Like waves of emerald green ribbons, the lights of the aurora borealis dance across the night sky. Even though these delights to the eye are best seen at night, they're caused by the sun. The green swaths form when solar winds, which are high-speed, electrified particles released by the sun, collide with the Earth's magnetic field. Some of the particles travel down the magnetic field lines into the Earth's geomagnetic poles. Here, the particles get trapped and start to collide with atoms in our atmosphere, releasing energy in the form of light. Oxygen releases red and green light, while hydrogen and helium atoms glow purple and blue. But auroras aren't just something that happen on Earth. In fact, these solar winds can also reach faraway planets like Jupiter. Using an ultraviolet camera, the Hubble telescope was able to capture the gas giant's immensely active auroras back in 2016. This is because Jupiter's magnetic field is 20,000 times stronger than Earth's, making its auroras so expansive that they can cover areas larger than our entire planet. And it's not just Jupiter that outshines Earth in the aurora arena. Saturn also sports some brilliant aurora ribbons around its poles. Captured through Hubble's ultraviolet lens in 2018, these appear to be blue. However, previous data collected from the Cassini probe indicated that, to the human eye, those ribbons actually look red and purple. Now that we've explored the auroras of Earth, Jupiter, and Saturn, which one do you think has the most mind-blowing illuminations? Cast your vote down in the comments below, and let's see who comes out on top. Nesting doll stars. You'd think the universe was big enough for every star to have plenty of space. But according to the Thorne-Zeitkow theory, some stars have no personal boundaries. Instead, they exist inside other larger stars like Russian nesting dolls. As impossible as it looks, there are two main theories that can explain this phenomenon, and neither of them involve popping the top off the larger one. It begins with a binary system, where two stellar bodies are gravitationally tied together. The more massive of the two stars explodes into a supernova, leaving a tiny, ultra-dense remnant called a neutron star. Over time, the remaining stellar body evolves into a red supergiant and slowly expands. If it does, the neutron star will spiral into the supergiant's center, where it will sit in the hot, gaseous shell of its host, a bit like a cosmic parasite. Another scenario theorizes that the energy from an explosive supernova could propel the neutron star into the red supergiant. Kind of like kicking a soccer ball into a goal. If the ball weighed as much as 2 suns, and the goal was a scorching 7,640 degrees Fahrenheit, God have mercy on that poor goalkeeper. Sunset strangeness. In 2015, the Curiosity rover sent back photos of a blue-skied sunset on Mars. That's right, blue. But during the day, these same skies are orange. It's the exact opposite of Earth. So how on Earth, or should I say Mars, does this work? Well, the sky on Earth is blue because of the molecules that make up our atmosphere. They partially block the sunlight and scatter it across the sky, but they're much better at scattering blue light's shorter wavelengths than red light's longer wavelengths. However, during a sunset, the sunlight travels through so much atmosphere that most of the blue light is scattered away, leaving behind awe-inspiring reds or oranges. However, it works a little differently on Mars. The red planet has a much thinner atmosphere that is filled with iron oxide dust, more commonly known as rust. It's this dust that gives the planet its distinctive red color. During the day, the red light is scattered through these particles, making the sky seem red or orange. But at dusk, the dust's density scatters most of the red light away. This means the shorter wavelengths of blue light can pierce through, giving the setting sun that incredible indigo halo. So, sunsets look pretty cool through different atmospheres, unless you're stuck on Venus. This hellishly volcanic planet has an atmosphere that's so thick that you couldn't even see the sun through it. To prove it, in 1981, the Soviet Venera probe sent back these images from the surface of Venus. The sky is a toxic shade of yellow, thanks to all the carbon dioxide and sulfuric acid clouds clogging up the atmosphere. So a sunset on Venus would look something like this, a bit like turning the dimmer switch down on the world's most garishly painted room. But what about planets without any atmosphere at all, like Mercury? Without any molecules to scatter the light, the sky would actually appear a lot like the sky on our moon. That is to say, completely black both day and night. Houston, I think we may have discovered the home world